Okay. Welcome everyone. We'll start with the event in 2-3 minutes. Hello everyone. Last month we had an online session on tracking SSTV from home. Many viewers received beautiful images from SSTV. But what is SSTV and what should everyone know about it? Today, I, Vaishnavi Agarwal, a member of the Ham Radio Club, IIT Bombay, welcome you all to the talk on slow scan television, what we all know as SSTV. SSTV, or the slow scan television, is a transmission protocol which is used for sending images over a voice bandwidth channel that makes it possible to send images over thousands of miles. Normal television, which is also referred to as FSTV or the fast scan television, transmits 25 to 30 frames per second, while SSTV travels only about 8 seconds to a couple of minutes to transfer one frame. Hence, the name slow scan television. The concept of SSTV was introduced by Copthorne MacDonald in 1957-58. He developed the first SSTV system using an electrostatic monitor and a Vidicon tube, that is a video camera tube. So where was it used? As you can see here, Luna 3 used SSTV to transmit the first images of the far side of the moon. We can observe that the first image that we received then using the SSTV and the recent images that we have received using the latest technology are very similar. The image showed the craters at the same positions. Hence, SSTV was very useful. Here you can observe the craters being at the similar positions. And then the Faith 7 camera of the spacecraft Faith 7 used in Mercury Atlas 9. The final crewed space mission of the US Mercury program transmitted one frame every 2 seconds with a resolution of 320 lines. The Apollo TV cameras used SSTV to transmit images from inside Apollo 7, Apollo 8 and Apollo 9, as well as the Apollo 11 lunar module television from the moon. So the images of Apollo 11, where you can see the astronauts, are gifts of SSTV too. Do you know? It is said that NASA had taken all the original tapes and erased them for use on subsequent missions. However, the Apollo 11 tape search and restoration team, formed in 2003, tracked down the highest quality films among the converted recordings of the first broadcast and brought them together, then contracted a specialist film restoration company to enhance the degraded black and white film and converted it into digital form. Having looked at the historical importance of SSTV, you must have questions on how this was done. This is what the transmission requires. A computer where your data is present in a digital form. The SSTV interface, which acts like a function to convert the digital data to analog and vice versa. We'll talk more on this ahead. And the transceiver, this receives and transmits the signals in analog form. SSTV interface encodes the data in which every different value of brightness in the image gets a different audio frequency. In other words, the signal frequency shifts up or down to designate brighter or darker pixels, respectively. Color is achieved by sending the brightness of each color component separately. In simpler words, a digital image in your desktop is converted to an audio signal, which is further converted to radio frequencies, that is the analog signal, and transmitted. This signal then received by a receiver and converted back to the original image. This protocol of communication is called SSTV. The SSTV interface encodes the digital data and converts it to a radio signal. It is like encrypting your data in a manner which can be decrypted or decoded into its original form by the SSTV interface on the other side of the communication process. There are different types of encoding procedures, which are called modes. Now, there are a number of different modes, but the most common ones are Martin M1, which is popular in Europe, and Scotty S1, used mostly in the USA. Using one of these, an image transfer takes 114 or 110 seconds. Some black and white modes take only 8 seconds to transfer an image. So what does this table tell you? Here, the color column tells you the color code that is used. That is the colors that are encoded or encrypted into signals. For example, in Scotty, the color code is RGB. That is, the colors red, green, and blue are encoded when this mode is used. An image can be considered as a collection of lines, or as we call it, scan lines. A high number indicates that a lot of information is transferred. This number is proportional to the time taken. The main difference in all the modes is the image quality, which is proportional to the time taken to transfer the image. As you can see in the slide here, PD120 is faster than PD180. Hence, the image quality is better in the case of PD180. So today, we will talk a little more on PD modes. PD modes are the result of a cooperation between Paul Turner and Don Rotter, which was first introduced in May 1996 and was developed to improve image quality. For speeding up the transmission, YCRCB color coding is used, unlike the use of RGB color coding in other modes. So what does YCRCB color coding mean? Just like in RGB color coding, the colors red, green, and blue were encoded. In YCRCB color coding, it is the brightness of yellow, which is also called the luminance, and a combination of RY or red yellow and BY or blue yellow, which is called the chrominance, are encoded. Before moving ahead to the time sequence of PD120 mode, there are some new terms that we will understand here. Sync pulse. It tells the cursor to come to its initial position or to the top left corner. It basically asks the cursor to create a complete image. Porch or sync porch. It tells the cursor to be in its leftmost position. If due to some noise the cursor gets placed at some coordinates other than the initial ones, it helps the cursor to get positioned in such a way that it creates a straight image and not a slant one. In case of PD120 mode, the steps take place for odd lines and even lines. What we mean here is that the first, third, fifth, and so on lines are odd lines, whereas the second, fourth, sixth, and so on lines are even lines. So this is how the mode proceeds. The scan line begins with 20 millisecond sync, where the cursor is positioned at its initial position. Then there is a 2.08 millisecond gap of black, that is the porch step, and the first luminance signal Y1. It is followed by 4 formats of slow scan TV transmission, 19 chrominance signals RY and BY without any gap. Then there is a second luminance Y2. In simpler words, there is a 20 millisecond pulse or signal that tells the cursor to get placed in its initial position, and a 2.08 millisecond long signal that is called the porch, which makes sure that it is in the leftmost position of the line. Then comes Y1, the signal which decodes yellow from the first line, the chrominance signal, that is RY and BY scan, which decodes these colors averaged from the first two lines. And then Y2, or the luminance signal, that decodes yellow from the second line. Here, the formula given can be looked at as the function used in the SSTV interface to decode and encode. It converts the color byte from the digital data to frequency of the analog data. Now that we have looked at the modes of encoding, what is it that tells decoder what mode to use? How does it come to know which mode was used to encode the data? So let's look at something that helps, the spectrogram. A spectrogram is a frequency versus time graph. It includes the following components: a calibration header, the VIS code, scan lines, and the sync pulse. A calibration header is sent before the image. It consists of a 300 millisecond signal at 1900 Hz, a 10 millisecond break at 1200 Hz, and another 300 millisecond signal at 1900 Hz, followed by a digital VIS, that is vertical interval signaling code, identifying the transmission mode used. The VIS consists of bits of 30 milliseconds in length. A transmission consists of horizontal lines scanned from left to right. The color components are set separately, one line after another. The color encoding and order of transmission can vary between modes. Most modes use an RGB color mode. Some modes are black and white with only one channel being sent. Other modes use a YC color mode, which consists of luminance Y and chrominance RY and BY, just like in the case of PD120. The modulating frequencies change between 1500 and 2300 Hz, corresponding to the intensity or the brightness of the color component. The image aspect ratio is conventionally 4:3. Lines usually end in a 1200 Hz horizontal synchronization pulse of 5 milliseconds after all components of the line have been sent. In some modes, the sync pulse lies in the middle of the line. So this is how the signal gets decoded. We can use a test card to check if the mode identified by the decoder is correct or not. If we get a slant image like this for the test card, or the colors are different, it implies that the mode is wrong. Sometimes, while decoding the signals, despite working in the correct mode, the image quality is poor. This happens because of the presence of some noise. The pictures look like this. We have seen working of SSTV now. We know what is happening and how it works. But what actually happens or helps us with the encrypting and decrypting business? These are the encoders and decoders. So we have encoders like MMSSTV for the PCs, SSTV encoder for the mobile phones, that is the Android or iOS, and embedded systems for the CAMs and SATs. On the other hand, for decoding, we have MMSSTV, RxSSTV for the PCs, and Robo36 for mobile phones. So let's do something. Install the Robo36 app on your phones. The link is shared in the YouTube description. By the time everyone installs the app, let us look at some questions that our viewers have asked. Try to get some other device so that you can play the sound. There is another link from AMSAT UK for the audio signals in the description. So we have one question here which says, can you tell the meaning of cursor? Okay. So here, when I said the cursor, this means like in this image, as you can see, this image is not a complete image. This is still getting decoded and being created here. So this image is created line by line. So the cursor meaning it is a thing, or you can call it a medium by which this image gets created. So the cursor, when it is given the sync pulse, it is told to go to this initial position, that is the top leftmost position. When it is given the sync port signal, then it is asked to go to the leftmost position. So you can also say that the cursor is a pen which draws this image here. I'll start the audio so that you understand it better. So this is the site whose link we have shared in our description. So as you can see here, we have two audio signals. From one is in PD 120 mode and other is PD 180 mode. So this signal or this audio clip that you heard right now, the signal that came in the start of the whole clip is the calibration header. So calibration header followed by the VIS code. This indicates the mode that is used. So this signal is different in the case of PD 180 mode. So I'll repeat. This is the calibration header followed by VIS code for PD 120 mode. And this is the calibration header followed by the VIS code for PD 180 mode. So by now you must have installed the app. So let's open Robo 36 and decode a few audios. So now you can see that I have opened my Robo 36 app. So now once this calibration header and the VIS code is complete, you can also see that the Robo 36 mode that was written on the left hand corner, here it changed to PD 120 mode. You can also observe that when the audio starts, the signal is different as compared to the signal later. Now we will decode the image. So when you start decoding, make sure that you have no noise or any disturbance around you. So you'll get a clear image. In my case, as I am streaming from both my phone and my laptop, there will be a lot of disturbance and a lot of distortion, due to which I'll not get a clear and a good quality image. So I'll try to decode the signal, but I'll also show you how the actual image looks like. Okay, so as you can see, I cannot decode this image right now because there's a lot of disturbance because of streaming. So what I suggest you is you try to decode this image and tag us and upload it on Facebook. Okay. So also you can observe here that PD 120, the audio signal is about 2 minutes long. And for PD 180, it is about 3 minutes long. So that means 120 is is 16 to 2, 120 seconds long audio signal, and 180 it takes around 180 seconds here. What differences are there?
Hello, Vaishnavi. Can you hear me? Yeah. Hello, Vaishnavi.
Yes?
Can you switch on the mic of your mobile phone? The audio is not audible.
Okay. So do you want me to decode it once again?
Yeah, yeah. Okay.
Okay. So we'll try doing it for PD 180 mode. Okay, so the problem still exists. Um, what we can do is we can move ahead right now. Okay, so these are the decoded images that I have received from these signals. So I'm audible. So what I was saying was these are the decoded images that I had received from these signals earlier. You can see that the quality of PD 180 image is much better than that of PD 120 image. There are some active SSTV programs that allow hams to receive signal from SSTV. AO92 was handed over to AMSAT in the year 2008 ARISS SSTV event for which we received an award. You can connect with us on different platforms like Instagram and Facebook. You can also follow us on WordPress and read blogs on ham radio and a lot more. You can fill this form to join our WhatsApp group. The code will be displayed here for some more time.
Hello, Vaishnavi.
Yes.
Yeah, so can you just repeat the time sequence part once again? The whole encoding techniques part.
Yeah. So this part, right?
Yeah, yeah.
Okay. So this is the time sequence, and how it proceeds is in the following manner. First, a sync pulse, which is 20 milliseconds long, or you can say a signal of 20 milliseconds long, that tells the cursor or the pen that is drawing the image, is asked to get placed in its initial position. Say if this is my image, then my cursor is asked to be placed here. But there may be a chance that there is some noise or a disturbance. So then again a signal of 2.08 millisecond, that is the porch or sync porch, that is given. So it tells, like, in case my cursor is placed here, then it tells the cursor to be placed to the leftmost position in the same line. So it gets placed like this. So it makes sure that the image is formed in a straight manner and not in a slanted form. The next, Y scan, that is the luminance signal that comes. So this is from the odd line. That is, it encodes or it decodes. Like if you are encoding the image to the signal, then it will encode all the yellow color on that line and put it and convert it into a signal. Again, then RY scan and BY scan, the chrominance signals will be created from the average of RY and BY from both first and second lines, so that they get converted to a signal or get encoded to the signal. Then comes the Y2. Y2 is the luminance signal or conversion of or encoding of the yellow light or the yellow color from the digital data to the um, analog data. So this is the method of encoding a line, first two lines of the image to signals. This is repeated until all the lines are encoded into a signal. And again, it happens that these are decoded in the similar fashion to an image. So this is the formula that one uses to convert the color bytes, that is from the digital data or the image on your desktop, to a frequency, that is the radio signals or radio frequencies.
Uh, okay, so I guess we can stop, but there is one announcement that I want to give. So on the 24th January of this month, 24th January, we will be conducting the ground station workshop, uh, and it will be open for all engineering students, and it will be assured that it is going to help any student who want to learn more about how to create or set up a ground station or even the basics of it. So maybe you could join us on 24th for that evening. Yeah, thank you.
Thank you everyone for attending today's session. Hope you have a great year ahead.